Hello, and welcome to our lesson on the graphs of trigonometric functions. In this lesson, we'll be revisiting our previous discussions on trigonometric functions, then delving into the reasons behind their specific graph shapes and the importance of these graphs. After gaining this insight, we'll explore some practical cases to apply our newfound knowledge, thus reinforcing our understanding through examples. So far, we've covered the basics of trigonometric functions in our geometry unit, where you became familiar with sine, cosine, and tangent. We discussed how these functions relate to the angles and sides of right-angled triangles. This foundation will now help us to transition to more advanced topics, specifically their graphical representations. Understanding the graphs of trigonometric functions is a vital technique used in various fields such as physics, engineering, and even economics. For instance, the sine wave graph is essential in studying wave motions and oscillations. Being able to visualize and interpret these graphs allows us to solve problems involving periodic phenomena, such as determining the height of a wave at a given point in time or predicting the future behavior of cyclical patterns. Let's get started. Let's begin with a review of the trigonometric functions. In right-angled triangles, we have three primary trigonometric functions: sine, cosine, and tangent. Usually, these terms are abbreviated. These functions relate the angles of the triangles to the ratios of their side lengths. The sine of an angle is the ratio of the length of the opposite side to the hypotenuse. The cosine of an angle is the ratio of the length of the adjacent side to the hypotenuse. And the tangent of an angle is the ratio of the length of the opposite side to the adjacent side. These functions take an angle as input and provide a ratio as output. Now, let's move on to tracking changes with trigonometric graphs by graphing these functions. A graph is a visual way to track changes. A trigonometric graph specifically tracks the changes in the trigonometric ratio as the angle changes. To create these graphs, we'll tweak our usual graph to plot angles on the x-axis instead of regular numerical values. This means our x-axis will show angles in degrees or radians, starting from 0 degrees and moving through 90 degrees, 180 degrees, and all the way past 360 degrees, which is like completing a full circle and starting over. Now, let's begin to think about constructing trigonometric graphs. We'll use a value table to help us determine what the graphs will look like. Consider this sine function. If we plot these points on a graph, we notice that the sine function creates a wave-like pattern that repeats every 360 degrees. This wave rises to a maximum of 1 at 90 degrees, returns to 0 at 180 degrees, falls to -1 at 270 degrees, and comes back to 0 at 360 degrees. For the cosine function, we get a slightly different set of values. Plotting these points shows that the cosine function also creates a wave, but it starts at 1 and follows a similar pattern of repeating every 360 degrees, moving through 1, 0, -1, 0, and back to 1. Lastly, the tangent function is a bit different. Here, the tangent function has points where it becomes undefined at 90 degrees and 270 degrees, causing vertical asymptotes. Between these points, the graph rises and falls sharply, showing a repeating pattern as well. Now, let's look at comparing sine and cos graphs. Let's start by looking more closely at the sine and cosine graphs. Notice that they both have a wave-like shape and repeat every 360 degrees. One crucial observation is that the cosine graph looks like the sine graph, but shifted to the left by 90 degrees. This means that we can transform a sine graph into a cosine graph by translating it horizontally. In our previous lessons, we learned that translating a graph means shifting it left or right, or up or down. So, if you take the sine graph and shift it 90 degrees to the left, you'll get the cosine graph. Similarly, if you shift the cosine graph 90 degrees to the right, you'll get the sine graph. Understanding these transformations helps us to see the deep relationship between these trigonometric functions and makes it easier to work with them in various mathematical contexts. By plotting these graphs and noting their properties, we're able to gain a visual and intuitive understanding of trigonometric functions. This understanding is crucial for solving problems in various fields that involve periodic patterns, such as engineering and physics. Great job following along so far. The graphical representation of trigonometric functions is not only vital for mathematical applications, but also provides a fascinating visual insight into how these functions behave. Let us begin with a simple problem involving the sine function. Sketch the graph of y is equal to the sine of x. We want to do this for one period, from 0 to 360 degrees. Step 1 is to identify the key points. For the sine function, we know that sine of 0 is equal to 0, sine of 90 is equal to 1, sine of 180 is equal to 0, sine of 270 is equal to -1, and sine of 360 is equal to 0. Next, plot these points on the graph. Your graph should have degrees on the x-axis from 0 to 360 and sine values on the y-axis from -1 to 1. Finally, connect these points smoothly with a wave-like curve. The sine graph starts at 0, 0, rises to 91. Then it comes back down to 180, 0, dips to 270, -1, and returns to 360, 0. This simple sketch helps us to visualize how the sine function behaves over one cycle. Our next example will involve finding the sine of a given angle, using the graph. Using the sine graph, determine the value of sine of 150 degrees. Step 1 is to locate the angle. Find 150 degrees on the x-axis of the sine graph. Step 2 is to read the value. Trace upwards from 150 degrees until you hit the curve. From this point on the curve, trace horizontally to the y-axis to read the corresponding sine value. From the graph, sine of 150 degrees is approximately 0.5. Our final example will involve solving a real-world problem. Here, a Ferris wheel's height above ground, h of t in meters, at time t seconds, can be modeled by the function h of t is equal to 10 plus 8 sine of pi t divided by 30. Determine the height of the Ferris wheel at t is equal to 15 seconds. Step 1 is to substitute the given time value. Plug t is equal to 15 into the function h of t, so you get the following. Step 2 is to simplify inside the sine function. Now, you have the following. Step 3 is to calculate the sine value. This gives you the following. And finally, step 4 is to find the height by substituting back into the original function. So, h of 15 is equal to 10 plus 8 multiplied by 1. This is equal to 10 plus 8, which is equal to 18 meters. So, at t is equal to 15 seconds, the Ferris wheel is 18 meters above the ground. A graph can help us visualize this more clearly. These simple examples illustrate how to approach GCSE level problems involving the graphs of trigonometric functions. Understanding these graphs will greatly assist you in solving a variety of mathematical and real-world problems. In today's lesson, we began by reviewing the basic definitions of these functions, and then moved on to understanding how their values change as the angle varies, which we visualized using graphs. We plotted the sine, cosine, and tangent functions, noting their wave-like patterns and periodic behavior. For the likes of sine and cosine, we observed how they repeat every 360 degrees, and how the cosine graph can be seen as a horizontally shifted version of the sine graph. The tangent graph presented vertical asymptotes, where the function becomes undefined, displaying a distinct repeating pattern. By comparing these graphs, we gained insight into their properties and transformations, such as horizontal shifts. This graphical understanding is crucial for solving problems involving periodic phenomena in various fields, like physics and engineering. Overall, we have reinforced our comprehension of trigonometric functions through their graphs, providing a visual and intuitive perspective that is essential for many mathematical and real-world applications. Watch the rest of the GCSE Maths course at Sophos Education.